Hello everyone, I'm Lawrence Sinks. I did some research on prime reciprocals and found some fascinating things. The first paper I read on this topic is by Amitabha Tripathi from the Indian Institute of Technology in Delhi, India. It explains the strange rotational symmetry I found in my circular number graphs from last video. As you can see, Tripathi noticed that if we break up the repeating digits into two equal blocks and add, we find that we get a number with only 9s. You can see that the symmetries present in these number diagrams already break up the decimals into two separate blocks. And the row of 9s in the sums makes sense. If I take the digits from across the circle in each diagram, I find they add up to the prime number in question, and the fraction they represent would, and should, always add up to 1. No matter which direction I go in, whether I start counting from 0 or 1, I should be able to find pairs of fractions that add up to 1 in the same order. This also explains why the number of repeating digits is always even, because you would have to pair the numbers together. What about weirder primes, like 2, 5, 11, and 37? Well, Nick H. Huang from China seems to answer this question in his paper from 2015. 11 and 37 are factors of numbers with repeating 1s, which is why the reciprocals were repeating 2-digit or 3-digit numbers. But this is a whole nother can of worms that I'll open another day in another video. What's more interesting is the nature of the numbers themselves. We normally write numbers in base 10, and computers write numbers in base 2 and 16. The reason some decimals repeat while others don't have to do with place values and what the place values really mean. Let's define the variable a as any rational decimal. It can be represented by the sum of all integer multiples of the negative powers of 10. And the series of x coefficients represents the digits in each place value, in each place of the decimal. This sum works for any base number b as well. If the denominator of any unit fraction, when completely factorized, only contains powers of 2 and 5, which themselves are the prime factors of 10, then its decimal form would terminate. Since k here would be finite, we would only need a finite number of digits in a series that adds up to the desired fraction. But if we throw in any primes that are not factors of 10, then things get a little more complicated. K would need to approach infinity. We would need an infinite series that merely converges to the desired fraction. This is why repeating decimals are so common, with even most even reciprocal fractions having repeating decimals. Nick H. Huang mentions this in his paper as well, as a follow-up to Fermat's low theorem that he also mentions earlier on. But all this still does not explain the weird paths themselves. Is there a rule? Is there a pattern? Would something else emerge with larger primes? Comment down below if you guys have any ideas to add. Anyways, thank you for watching. Please like and subscribe if you enjoyed. I'll see you guys next time.